Yeah, so I primarily wanted you folks to discover what might be more interesting to work on in the coming days. Maybe it could turn out as your next big project idea. And many of the topics that we are going to discuss in this talk will be equally applicable to any other modalities of data where deep learning has shown great promise, such as natural language processing, speech data, and so on. And also another objective is to help you get up to speed with some of the most cutting edge stuff that's happening around in this area. So yeah, without further ado, let's get started. So the first trend I am observing for quite some time now is the community is focusing more and more, toward resource efficient models. And let's start by why that might be the case. Because if you have your motivations right, it becomes so much easier to work around that, around those motivations. So the first point is, state of the art computer vision models are often very hard to run offline on tiny devices such as mobile phones, Raspberry Pis, and other microprocessor devices. And it's a fact that mobile devices, mobile applications like Prisma, Google Photos, and so on, they make use of pretty heavy machine learning machinery, right? If you have noticed carefully, and most of the things that run inside those applications in a machine learning context often they are run offline, and you cannot possibly expect an application to be containing probably 1 GB or 2 GB model, because that size is not going to qualify for Play Store or even App Store requirements. So if you have developed a state of the art model, that's great, you should definitely celebrate it. But when it comes to deploying that state of the art model into tiny devices such as mobile phones, it might often get difficult if you do not have its efficiency, model size, and other performance metrics right into the context. And the heavier your model is, the more latency it would have. And by latency, I mean inference latency. And by inference latency, I mean the time it takes for a model to run a single forward pass, right? Essentially, for mobile devices, we would want it to be as fast as possible, because in a mobile application, probably users would like to get instantaneous results. That's the entire point of using mobile devices, right? So just as I mentioned, heavier models tend to have significant amount of inference latency, which is a sort of a shame for mobile applications. And also, heavier models will and can affect the infrastructure costs significantly. And going by Murphy's law, if something may have happened, it will happen eventually. So consider a situation where you have a requirement to deploy a model that has a size of probably 500 GB, and 500 GB models are not very rare. If you take a look into the full blown GPT-3 model, it's around that size, right? And also switch transformers, which has trillions of parameters inside it. So, and it's not very cost effective to host these models in a remote capacity and run any prediction payload around them. So eventually your infrastructure costs to deploy these models and host these models, the costs are going to turn way up. So it's naturally a good practice to try to think of ways in which you can optimize your model further and also be able to retain its original performance as much as possible. Because in mission critical applications, you wouldn't want to lose any of the performance aspects of the model, but at the same time you would also want it to run as fast as possible. So I hope I made the grounds quite clear as to why resource efficient models are currently a requirement for many use cases. And of course, think about a situation where cloud-based model hosting is not really an option. There may be cost-related issues. There might be network connectivity-related issues. There might be privacy concerns in the first place. What if those requirements are stringent, and what if they are meant to be met at any cost? So again, offline models are the way to go forward in those situations, right? So any questions at this point in time? Yeah, feel free to use the chat or unmute yourself and just ask away if you have any questions. Otherwise, we'll just continue. Okay, we'll continue then. Uh, so first trend in resource efficient models is sparse training, and what that is, imagine training with matrices that have lots of zeros. And the reason why I'm mentioning matrices, because neural networks are primarily based on matrices, like be it fully connected dense networks, be it convolutional neural networks, be it recurrent neural networks, or any neural network for that matter. They are primarily based on one data structure, that is matrices, right? And imagine training a neural network that has matrices containing lots of zeros, right? So that's what a sparse tensor is. And why introducing lots of zeros might make sense, because often neural networks are exposed to very high dimensional data, because image data are often very high dimensional. Not often, image data is high dimensional, actually continuous high dimensional data. So introducing lots of zeros here might be beneficial, because not all the dimension in the projection space are interacting with others in in an equal manner, right? So if you introduce lots of zeros in your matrices during the initialization time, performance might take a hit, but you also get a major reduction in the number of multiplications, because we have all the clever tricks of vector multiplications that can benefit from this fact that our matrices have lots of zeros. We can essentially compress many matrices and do the multiplication way quicker, right? And with the modern machine learning cavalry, it's also possible to have your neural networks contain lots of zeros, but at the same time train them in a way that would yield the maximum sort of performance out of that configuration. So here's a visualization of how a sparse matrix might look like with different sparsity factors. And I hope the point on sparsity is clear now. If it's not, feel free to let me know in the chat. So one very closely related technique is pruning, where you sort of discard network parameters that are below a certain threshold. Although other criteria exist as well, just beside magnitude thresholding, there are other techniques as well, such as adaptive thresholding and so on. And here are a few good reads if you are interested in checking out what sparse training really is. One is lottery ticket hypothesis. And if you are interested to try out the pruning APIs available inside the TensorFlow model optimization toolkit, I have also linked a very useful resource in that matter. So yeah. So proceeding forward, the next topic in resource efficient model training is post training inference, where you already have a sort of trained model. Now you want to further optimize it to get as minimum inference latency as possible, and at the same time you would also like to ensure the original performance is retained as much as possible. So the first source of truth here is lower precision models with quantization. And by lower precision, I mean floating point 16, integer 8, and so on. So typically neural networks are trained using floating point 32 precision, and it's a no-brainer that having some lower precision to express all the model parameters will definitely result into a lower sized model, right? But also performance can take a hit, because if we lower the precision of neural networks, the parameters might miss out on the expressibility part, right? And there's to compensate for that fact that that post training quantization or having your neural network parameters expressed in a lower precision format might actually induce some kind of information loss. Quantization aware training can help to compensate for that information loss. And it's absolutely possible to also, combine pruning and quantization at the same time to get the best out of the both worlds and yield a very small sized model which is performant enough for many use cases. And here are some few good reads. Post training quantization is very gracefully available via the TensorFlow Lite API. So I highly encourage you folks to check it out if you have any relevant use case. And also quantization aware training is now absolutely available via the TensorFlow model optimization toolkit. You just need to make very few lines of code. Make a very few changes in your total lines of code, and you can get a model up and running with quantization aware training in no time. So yeah. So another very relevant topic around the area of resource efficient models is knowledge distillation, and it's been around for quite some time now. It was popularized by Geoffrey Hinton and a team of other Google Brain researchers around 2015. So the basic idea is we first need to train a very high performing teacher model, then distill its so-called dark knowledge or just knowledge by training another smaller student model to match the labels yielded by the teacher. So generally what we do is we have some kind of supervised data set and we train our neural networks to minimize the loss between the ground truth labels and the labels predicted by the neural networks, right? So we have this ground truth coming from subject matter experts or from others, other sources of truth. But in the case of knowledge distillation, these ground truth labels come from a teacher model. So in that way, it's shown that it's able to sort of, the system is able to sort of distill all the knowledge that the teacher model has into a smaller student model, and practically this technique just works wonders. So I highly encourage you folks to take a look into this if you are interested. And here are a few good reads. If you follow keras.io examples, there's already an official implementation of knowledge distillation there. So yeah. And here are some few notes that I think might be helpful for you folks. So other post training optimization techniques exist, and one such very practically oriented technique is weight clustering. And there's also, quite some research around the area of hardware aware neural architecture search, where you guide your search with constraints like, hey, I'm going to deploy this model on a resource constraint hardware, so I want you to, yield models that respect that criteria. So that's what is called hardware aware neural architecture search. And some here are some models uh, that that were sort of generated using this technique. One is mobile.it, which is sort of state of the art in mobile object in the space of mobile object detection models. MobileNet v3, another great model when it comes to mobile image classification models. RegNets are also great, and recently came EfficientNet v2, which is sort of currently the state of the art in image classification for mobile devices. Yeah, so my point is, with experience you will learn to combine different techniques discussed so far. And here's one recipe that has worked well in my experience. Basically the idea is to train a bigger and high performing teacher model, perform knowledge distillation, preferably using quantization aware training, because ultimately if your goal is to deploy it on a mobile device, you would likely use quantization, and you wouldn't want your model to incur any information loss that's induced for post training quantization. So it's always good to sort of train your student model using quantization aware training. And you could also train your teacher model using quantization aware training, but know that quantization aware training is very expensive. So yeah, you would want to be able to make the best use of your resources. And then of course prune and quantize the distilled model and deploy and enjoy. So yeah, any questions? All right, I guess there aren't any questions. So the next trend I have been noticing is generative deep learning for very creative applications. So the kind of things that we see in Prisma is they're coming from a generative model, and the applications are highly creative. We must agree on that. So I also wanted to sort of discuss the space of generative deep learning for creative applications. So yeah, let's get started. So to set things right into perspective, generative deep learning has really come a long way. So back in 2014, on the left hand side, we can see some faces appearing, but the quality is not really good. And on the right hand side, we are seeing faces of people that do not even exist, and these faces are generated by state of the art generative adversarial networks, and it's very hard. I mean, it's almost impossible for human beings to tell that these persons do not exist. And as a matter of fact, there actually exists a website called This Person Does Not Exist. And let's see how that looks like. So every time you refresh this particular website, it's gonna give you a face of a person that literally does not exist. So let's see. These people do not exist. So yeah, as you can see in the footnote, it's generated by a model developed by the folks at NVIDIA. It's called StyleGAN V2. So it's an amazing work. So if you are interested in this space, I highly encourage you folks to check it out. Okay, back to business. Yeah. So the next point I have observed in the space of generative deep learning is lots of creative application, and some are quite practically oriented actually. So consider the task of image super resolution, which is highly relevant in applications like surveillance and so on, right? Where you typically have a very low quality, low resolution image, and to be able to make better, perform better surveillance, you would want to be able to upscale it in a salient manner. So on the lower left hand side, we are able to see output of a generative adversarial network that has upscaled the low resolution image, which is quite close to the original image. And on the lower right hand side, we can see the naive bicubic resizing, which is not anywhere near the quality of the output generated by the ESR GAN, right? So this is the kind of promise that comes with image super resolution models of the modern day. And there's another very noticeable trend is domain transfer, where you have some sort of natural image and you would want to be able to transfer that image into some other domain, maybe the cartoonized version of that natural image. Maybe you wanted to take a selfie and sort of convert that into a plausible into a visually plausible anime, or even just run things like Prisma, like stylize your image or so on. So it's also called domain transfer, broadly speaking. So yeah, here are some applications that I personally have worked with one of my fellow friends, Margaret. So yeah, I have also linked to the tutorials where you can know more about this application. So yeah, another task is image extrapolation, where you have sort of masked out a certain portion of some image, preferably a natural image, and you want to be able to generate novel sort of context for that masked out region, as you can see in the figure in the slide, right? So it's highly applicable for domains like image editing. This is precisely what many features in Photoshop would allow you to do, and it's now possible with the use of models like Boundless, which is essentially a generative adversarial network. And there's also a noticeable trend around implicit neural representations and something called CLIP, which stands for contrastive language image pre-training. And what if I told you this image was generated by this caption, live during plague? So the image that we are currently seeing was actually generated from this caption. Yeah, isn't this amazing? So again, a generative model at its very heart, and by combining two different worlds of implicit neural representations and CLIP was actually open sourced by OpenAI a few months ago in 2021, and we can get something as salient as this one. It has the capability of interpreting natural language and generate novel images out of it. So think of all the cool applications that we can, create around this things. So yeah, any questions?
Shayad, we can take questions at last of the evening.
Yeah, cool. Yeah, so some notes and suggestions in this regard. I would highly encourage you folks to study these works if this seems like exciting or interesting to you, and implement them. Actually, you can skip a few parts, only consider the bits proposed in this works that you genuinely like, but get hands on when you are studying these frameworks and implement them to in some minimal capacity and open source your work, because that will help you to build your portfolio in a very solidified manner. Maybe also develop an end-to-end project, because if you noticed, this project is an end-to-end project, and it combines many different things happening around the space of generative deep learning. And this end-to-end project has got many followers. It has got thousands of stars in the GitHub repository. Like, this is the repository of this project, Deep Days. So it's absolutely encouraging to see if you folks could develop an end-to-end project around these things, and also try improving their elements if you have found any, and who knows, you may find something novel and publish your work in a tier 1 conference. And the third trend is self-supervised learning, where you do not, make use of any ground truth labels. You make use of, pretext tasks, and you take a large chunk of unlabeled data set, and then you sort of ask your model to learn representations in a self-supervised manner. And Ian Lekan has been, popularizing this since forever now. So yeah, let's take a look into what self-supervised learning is. So first, let's discuss what are the stakes of supervised learning, because it's so practically oriented and so widely used across many different industries, right? So humongous amount of label data is needed to push the performance of supervised learning methods, and label data is often very costly to prepare and can be biased as well, right? You need to form a team of subject matter experts to label your data in a very rigorous manner, which is very time consuming, and it will burn your dollars, right? It's very costly as well. And the length of training time is very high when you have very large data regimes. And in the figures, we are able to see the kind of training schedules it takes to train a model on datasets like ImageNet 21K or JFT 300, which has got 300 million images, not like 1 million, 300 million images, right? So you get the idea. So here's the core idea behind self-supervised learning. So learning with unlabeled data requires you to ask your model to be invariant with different views of the same image, because if your model can figure out what truly differentiates these two views that are essentially coming from the same image, then it should be hoped that your model will learn to exploit all the meaningful semantic content present inside these images, and that is what we exactly need, right? And when you ask your model to be invariant to different views of same images, your model, as I mentioned, learns content that makes two images visually different. That is, consider a pair of cat and a mountain. Your model will be able to distinguish what are those components that differentiates a cat and a mountain, right? And preparing unlabeled data is way cheaper. Basically, internet is your is a is an unlimited source of unlabeled data. Of course, for natural images, if you are working in medical domains, this is still relevant, because unlabeled data set, preparing an unlabeled data set is any day cheaper, right? And you are of course asking yourselves, how effective is this approach? So almost as good as supervised learning, but sometimes even better, as you can see. So in this instance, we have a self-supervised learning method called SWAV by Facebook AI Research, which is almost as good as supervised. The green curve that we see in the graph is by a supervised learning method, and the orange one is coming from a self-supervised method. We can see the gap is closing in, right? And now in 2021, it's even better. We are able to see that the orange line, which is coming from a self-supervised learning method, it's able to even beat the performance of supervised learning methods. And this is something that genuinely excites me, right? For all the right reasons that we just discussed. And it's even more label efficient. So the meaning of label efficiency is when you have access to a labeled data set. If you have pre-trained your model on a large corpus of unlabeled data using some self-supervised objective, if you have access to 1% labeled data set, those models trained using self-supervised learning methods will perform better than vanilla supervised pre-training, right? Standard ImageNet 1K pre-training. So all in all, this is a very promising field, and this is where most of the vision research is happening in these days. So 2021 will be the perfect time for you to invest into self-supervised learning method, and also just explore the different methods existing around this area. So you also might be asking, these results are all for image classification, but computer vision does not only constitute image classification, right? It has got other tasks like semantic segmentation, object detection, and so on. So is it just for image classification? And apparently not. In fact, self-supervised methods are better than their supervised counterparts when it comes to object detection and semantic segmentation. So yeah, feel free to check these things out. And SEER, that is SEER, is currently the state of the art in self-supervision, and it's again a model from Facebook AI Research trained on 1 billion images. So yeah, let me have some water. Okay. So, what are the challenges in self supervised learning so far? Self supervised learning requires a very large data regime. Of course, it's unlabeled data to perform well for real world tasks such as image classification, object detection, and so on. But for domains like medical imaging, gathering a very large corpus of data might be very difficult. And contrastive self-supervised learning is still computationally expensive. Training these models using self-supervised objective is very computationally expensive, is what I wanted to say. And here are some good reads. The first one is from Jan Lekan and Ishan Mishra. It's an official Facebook AI research blog, and the second one is a new reps paper. So yeah. And the pre-final, this is going to be the pre-final trend we will be discussing: the use of transformers and self-attention for modeling computer vision problems. And I have cited this paper called "An Image is Worth 16 cross 16 words: Transformers for image recognition at scale" from Google Research, just for the sole purpose of this, because it has got a pretty wacky and cool title to it. I mean, an image is worth 16 cross 16 words. It has some poetic notion to it, right? So yeah. So basically, what attention is, it helps a network learn to align important contexts inside data by quantifying pairwise entity interactions. So consider an image consisting of different objects. Maybe in an image there are cars, there are motorbikes, there are cycles, and so on. So how are these entities related with each other? And also, is it absolutely important for a model to pay attention to all these objects equally, or should it put some weights in its attention, because when we see a natural image, we tend to pay our attention to a particular set of objects present inside that natural image, and not on all the objects present inside, to infer some decision what might be present inside that image, right? So this is what precisely attention does. It helps us to quantify these pairwise entity interactions and put some weightage in the attention space of the model. And consider this. This is a very plausible visual example to explain what attention is. So here's a caption. The person is riding a surfboard in the ocean. And as you can see, as we are making progress in the caption space, the model is able to, direct its attention where it's relevant with respect to the caption, right? In the surfboard, it's able to focus only on the surfboard. For the person, it's able to not accurately but still focus on the person. Isn't it absolutely amazing? So that's the kind of power attention brings into the picture. All right. So the idea of attention has been there in computer vision in many forms, like global context blocks, squeeze and excitation networks, or channel attention, and so on. But their gains have been pretty marginal at this point in time. And self-attention blocks actually form the basis of transformers. So the pros with self-attention, with pure self-attention based networks, we do not have any convolutions actually, right? So that means we do not have to design inductive priors, and hence transformers can be thought of as a general computation primitive for different learning tasks. Basically we need to stack multiple transformer blocks, and throw data at it and figure out what's relevant for it, right? And parameter efficiency with performance gains. And in the figure, we are able to see that with lesser parameters and by the virtue of self attention, it's able to compare state of the art performance with respect to state of the art convolutional neural networks. So this is a big gain in my opinion. But there are cons as well. The importance of large data regimes is paramount during training these transformer models, because transformers do not have well-defined inductive priors like convolutions, right? So inductive prior means we are basically enforcing our prior knowledge of the problem inside the network while designing its topology, right? Convolutions are great at exploiting locality, and that's what is needed to learn something from image data, right? We know that similar looking pixels are somewhere nearby inside a particular image, and this is exactly what locality of reference means. So yeah. And there are some recent improvements that would allow us to use a small data regime such as ImageNet 1 can still able to compare to state of the art performance on par with convolutional neural networks, date, LVWIT, and swing transformers. So feel free to check this out as well. And another trend is when self-attention is combined with convolutional neural networks, they establish very strong baselines. And this is a network that actually does this, called botnet. So here's an example. So in the standard residual bottleneck, we have standard convolutional layers with varying amount of filtered sizes. And on the right hand side, we have these bottleneck layers replaced with multi-head self-attention layers and nothing else, right? We have 512 blocks. It's just that these are now multi-head self-attention layers and nothing else. We have replaced 3x3 convolutions with self-attention layers. That's it. And it's able to, even generate performance better than pure convolutional layers. So it's really exciting to work in these areas, at least in 2021. Cool. And here's some, vision transformers for your perusal. If you want to explore this and have fun, please, please consider checking out these links. And the final trend I have been observing here is robust vision models. So yeah, let's see what that is. The problem is neural networks can be very brittle to imperceptible changes in input data. So this image perfectly, conveys this idea. On the left hand side, we have an image of a pig, right? The network is able to classify it as a pig with utmost confidence. But if we add very little amount of noise to it, it essentially results into an image of a pig. We are not able to see any difference on the right hand side figure, right? But it can fool a network into believing that this image is of an airliner, which is a blasphemy, right? So that's what precisely the idea is around the brittleness of neural networks to imperceptible changes in input data. And also, think of applications like self-driving car, where a pedestrian maybe got predicted as an empty road. Think of the kind of implications it would have on the company that got that prediction wrong, right? So yeah, these are very essential aspects when you are deploying vision models that has, you know safety critical aspects into it. So another part is corruptions. Deep models can easily latch into high frequency regions that actually make them brittle to common corruptions like blur, contrast, zooms, and stuff. So here are some examples. All of these examples are seemingly very similar to our human eyes, but for a model, they are entirely different things, and these little corruptions can, you know cause a model to misclassify these images, which is not really ideal. Okay, so there are also this aspect of out of distribution data, and there are two kinds of out of distribution data. One is where the domain is shifted but the label is intact, right? So on the left hand side we have natural images, and on the right hand side we have renditions like cartoonized versions and so on. So but the labels are entirely same. So consider this cartoonized image. This is an image of some chicken, right? But on the left hand side we have more naturalistic images, but the labels are same. Ideally you would want your model to be consistent around this shifts, right? So as I mentioned, we want our models to perform consistently with respect to its training. And there are also anomalies, right? Ideally, when when your model is, is met with some data or some distribution of data it hasn't seen during its training, it should yield very low confidence prediction, not very high confidence prediction, because these are anomalies, and it should know when it's wrong. So going by going by a modified quotation by Balaji Lakshminarayanan at New Rips. Basically, the quotation is all models are wrong, but some are useful, by John Firth. But here's Balaji's variant is what I prefer more. All models are wrong, but models that know when they are wrong are useful. So ideally, we would want our models to exactly, tell us, hey, I am not confident about this anomalous data points. Maybe you should look into these data points and figure out if they are anomalies in the first place. So that's what the idea is. And regarding perturbations, here are some solutions. Adversarial training can help very much. If you train your model in an adversarial aware way to make it aware of the adversarial perturbations it might meet during its inference time, it's great. It's like analogous to something in distributed training called Byzantine fault tolerance, where you prepare your systems to handle themselves when they are met with absolute worst conditions. And here's an amazing read: adversarial examples improve image recognition in the first place. So yeah. And here are some other notable defense techniques as well, like neural structure learning, denoise smoothing, and so on. And some solutions to corruptions. Consistency regularization is one of the most practically, employable techniques. Basically, it forces the fact that we want our models to be consistent under noised inputs, right? It should not affect our model's predictions if they are made with, very subtle noise like corruptions. Random augment can be very useful to, impose this regularization constraints. Noisy student training is another training method that can be highly helpful. Fixed match and also unadversarial example. This is comparatively new from Microsoft research. It came out around 2021, so it's another very, unconventional technique. So what about out of distribution data? Detect the anomalous points right away. Just as I mentioned, you want your models to be, generate very low confidence predictions on these anomalies. And also generalized odin, which stands for out of distribution detector for neural networks. That's also a very well tested and tried method. Okay, that's the end of my presentation.